Okay, I'm going to review chi-square calculations briefly. Recall that the chi-square test function, or purpose, is to compare your observed data and compare that to your expected data, and to tell you, using statistics, to tell you whether or not your observations, your observed data, are close enough to what you expect that you can accept them or reject them. So this is sometimes referred to as the null hypothesis. If you imagine any situation, you have a hypothesis, the actual data you get are going to be probably, just by random chance, a little bit off, even if you know you're right. And so how far off can it be before you begin to suspect that maybe your hypothesis is wrong? This is what the chi-square test helps you to judge. Okay, so if we, the null hypothesis then simply says the variation we see is not important. It's small enough that it's close enough to the expectation that we can accept the null hypothesis that those differences are unimportant. So I'm going to posit here that I'm doing a breeding experiment, and I'm going to breed some pink tribbles, and I'm going to breed some green tribbles. And so if I breed a pink tribble and a green tribble together, what happens? I get a pink tribble. Well, actually, if you know anything about tribbles at all, I get a whole bunch of tribbles, but they're pink. And so my hypothesis is going to be, well, let's keep it simple. I assume there's a single gene involved with two different alleles. And big P is pink, and little p is green, and the heterozygous tribbles are big P. And big P is dominant, so they look pink. That's my hypothesis. Okay, so I predict then that if I cross, let me go just to black here so I don't keep flipping back and forth with colors. If I cross a heterozygote with another heterozygote, then I'm going to get out of that the standard 3-to-1 ratio of color, this 3-to-1 phenotypic ratio. I could have big P or little p alleles. The other parent could give big P or little p alleles. I'm going to get 1/4 are going to be homozygous big P, 1/4 are going to be homozygous little p, and the remaining 2/4, or half, are going to be heterozygotes. But I'm going to have a total of 3/4 of them looking pink and only 1/4 of them looking green. That's my hypothesis, or that's what I expect, assuming my hypothesis is correct. Okay, so what actually happens when I do this? I've got two classes. I've got pink tribbles and I got green tribbles that I'm looking at. And so I do my cross and I observe 36 pink tribbles and 17 green tribbles. Is that close enough to a 3-to-1 ratio that I'm happy with my simple assumption of a single gene and two alleles? Well, okay, let's see. First of all, how many tribbles do I have altogether? I have a total of 53, a fairly small clutch of tribbles. And so if I am testing, or if I'm calculating now my expected number, I take 3/4, 3-to-1 ratio, 3/4 of them should be pink and 1/4 of them should be green. And of that 53, how much is 3/4 of that? Now, I do not put here 0.75, I do not put here 3/4, anything like that. That's just wrong, and that's just going to get me in all sorts of trouble. It's very important that I use the actual number that I observed, 53 in this case, and I indicate the proportions that I expect from using, in this particular case, a 3-to-1 ratio. And so 3/4 of 53 is 39.75. I, of course, can't have 3/4 of a tribble, but again, the expectation doesn't have to hew to integers. And 1/4 of 53 is 13.25. Let's just make sure that we got this right here. 39 plus 13 is 52, and another 1 is 53. So yes, that adds up to 53 as it should. Okay, great. Subtract, what's the difference between the observed and the expected? It doesn't matter whether you go observed minus expected or expected minus observed or bigger numbers minus smaller numbers. It's all going to get squared away anyway. Squared away. So the difference here is 3.75, and the difference here is going to be 3.75. I square those and round them to 14.06 for each. And then importantly, I take that value, the difference squared, and divide by the expected. Okay, the expected for the pink was 39.75. And so if I divide, and again round, I get 0.35 for the pink, and I get 1.06 for the green. I sum that up, and I get 1.41. Okay, so that's my chi-square value for this particular experiment. And what does that tell me? Okay, one other thing that you need to be alert to or aware of is the number of classes that you've got, and this is because it affects the number of degrees of freedom. If you were to walk up to somebody and say, I just did a triple breeding experiment and I got 53 triples, some are pink and some are green, how many of each did I get? They're not going to know. You could get 53 pink and 0 green, you could get 52 pink and 0 and 1 green, etc., etc., etc. But if you say I got 53 triples and 36 of them are pink, then, assuming the person can add or subtract, they will be able to figure out immediately that you had 17 green ones. So the degrees of freedom in an experiment is equal to the number of classes, in this case 2, minus 1. And, okay, 2 minus 1 is 1. So the degrees of freedom for this experiment equals 1. Okay. Now, if we look at the chi-square table, we note that there's this one column here under 0.05 that's highlighted in gray. That's because this is the standard probability value that essentially you always use. I mean, unless you know statistics. And so, I certainly don't know them well enough to mess with 0.05, we're good. 0.05, 5%. What that means is that we accept that this is not perfect. No system is. And so we're going to be wrong one time in 20. If we did, on average, 20 chi-square tests, one of them would give us the wrong answer. You can't know which one, of course, but and so that's what that 0.05 signifies. We could, if we were really paranoid, just say, I insist on a 0.01 or a 0.001. I insist on more confidence. Okay, but that's going to require more data and more work. And so 5% is a value that researchers have sort of agreed upon, and so it's the conventional standard. So that column is the 0.05 column, and then over here on the left you see degrees of freedom, and we've got 1 degree of freedom, so we simply read across the table. So the key value here for us is this 3.84. That's the threshold value for any experiment with 1 degree of freedom at a 5% p-value. Okay, what is that threshold? Imagine that the data that you got perfectly matched. It was a perfect match to your expectation. Then the difference between observed and expected is 0. The square of 0 is 0. Divide 0 by anything, you get 0. So your chi-square number that you got out of that calculation would be 0. So a small number like 0 means perfect match. A large number, conversely, means not a good match, a really bad match. This threshold tells you, for your experimental conditions, where to draw the line. So if I've got a value of 0, it's a perfect match. If my value for chi-square is smaller than 3.84, then I'm good. And I as they say down here at the bottom, I could fail to reject the null hypothesis or the chance hypothesis, which is failing to reject is a little confusing, but basically I accept it. The numbers are close enough, I'm close enough to 0, it's good enough, I'm below the threshold that my data are good enough, close enough to expected that I'm happy with them and I'm going to keep going. If my data were bigger, then I'd be down here with rejecting the chance hypothesis, and I'd say, well, something's wrong here, and maybe my hypothesis is wrong, and let me go back and retest. So our value, you may recall, was 1.41. That's smaller than 3.84, so our data are close enough to the expectation that we say, we're good with that. We're going to go along with our hypothesis that fur color in tribbles is controlled by a single gene with 2 alleles, at least if we're talking green and pink. All right, now let's make things a little more complicated, however. Things are never complicated enough. And let's say we have 2 genes we're worried about. We're concerned about color, just as we were before. We're still looking at pink and green, big P, little p. And we're looking at fur length as well. We've got long furred tribbles and we've got short furred tribbles. And so big L big L is dominant over little l, long fur is dominant over short fur. And so if we have a double heterozygote like this and crossed it to another double heterozygote, we would have how many different phenotypes coming out? We'd have 4. It could be green, it could be pink, could have long hair, it could have short fur. Right? So it's either green and long, green and short, pink and long, pink and short. But the ratios that we expect to get are not 1 to 1 to 1 to 1. We don't expect to see even numbers of each of those, because if we put together a quick Punnett square, probably not big enough given all the P's and L's going on here, but let's see what happens. So remember also that each column or row represents a gamete. This is something I see students have trouble with frequently. It is not P here and little p here and big L here and little l there, for example. See if I can erase that. Each gamete each gamete is going to contain a p allele, either big P or little p, and it's going to contain an L allele, either big L or little l. So one possibility is big P big L, or big P little l, or little p big L, or little p little l. And then the other one is also a double heterozygote, so it's going to have exactly the same possibilities, big P big L, big P little l, little p big L, or little p little l. And if you fill out the Punnett square, there's a total of 16 squares. You get a total of 9 that are going to be pink and something. They could either be big P or big P little p. We're looking at phenotypes here, so I don't care what the other genotype is. And they're going to be they're going to have long fur. So 9 out of 16 are going to have long pink fur. 3 out of 16 are going to have short pink fur. 3 out of 16 are going to have long green fur, and 1 out of 16 is going to have short green fur. So we expect to get a 9 to 3 to 3 to 1 ratio out of this. Okay. Well, okay. So let's do that. So we do that experiment, and we have 4 classes here. We have pink and long. We have pink and short. We have green and long. And we have green and short. And we breed a whole bunch of double heterozygous triples together, and we observe 112 pink long, 25 pink short, 24 green long, and 16 green short. That's our data. Now, using a chi-square test, how close are we? Are we correct in our assumption that we're dealing with 2 genes that are independently inherited, and a single gene for length with 2 alleles and a single gene for color with 2 alleles. Total number of triples that we're looking at is 177. And so 9/16, we expect, again, pink long should be 9/16 of the total. 9/16 of that is 99.56. And we expect to get 33.19 and 33.19, a little rounding here, and we expect to get 11.06 of the green shorts. And so that should add up to 177, and it'll be off a little bit because of rounding, I think, but let's see. 20, 40, 12, no, maybe it'll be exactly right. But yes, 177. Okay, so again, the math is the same as before. 12.44 with rounding, negative 8.19, and again, negative 9.19, and 4.9, 4.94 actually. Okay, I square all those values and I get 154.69, and I get 67.04, and oops, that's a 4, doesn't matter, 84.41, and 24.38. I divide each of those by the expected values, and I get 1.55, I get 2.02, I get 2.54, and I get 2.2. Add all those up, and I get 8.31. Okay, so all I need to do is calculate my degrees of freedom and then look at the table. So 8.31 is my chi-square value. How many degrees of freedom do I have? And again, it's the number of classes minus 1. In this case, the number of classes that I'm looking at is 4. Pink long, pink short, green long, green short. So 4 minus 1 tells me that the degrees of freedom here are 3. So now I've got 3 degrees of freedom, and I still want to use the 0.05, the 5% table. So my value, my cutoff value is 7.82. The value that I actually got from those data was 8.31, which is larger than 7.82, so something's wrong. The data that I observe are not close enough to my expectation that I'm confident that my hypothesis is right. So it's kind of close, but it's not there. One thing I could do would be to repeat the experiment, possibly with more tribbles. Or I could just throw up my hands and say, okay, it doesn't match, and let me think of a different hypothesis. But either way, that's what the chi-squared value is telling us. The data do not match closely enough that I can accept them, and so I'm forced to reject the null hypothesis and say, if the statistics are right, then there's something going on. It's not just chance fluctuation, which is giving me this deviation from my expectation.